Hello everyone, my name is Young-Jin from Korea Electrotechnology Research Institute. My topic is analysis of proximity and the skin effect and optimal design of effective coils and magnetic coupled wireless power transfer. In my talk, I will give a brief introduction of magnetically coupled wireless power transfer. I will also show the relation between coupling efficiency and the coil specifications. In addition, I will explain shortly the effect, skin effect and proximity effect in metal wires, especially in higher frequency. First, I will explain optimization of circular wire coils by calculating AC resistance for parallel state wire conductors. Second, I will show the optimization of pattern coils calculating AC resistance using volume filamentary models. For example, I will show the analysis of parallel state pattern conductors, and I will explain how to optimize printed circular and scale pattern coils. And conclusion is follows. This picture shows a simple configuration of a magnetic coupled wireless power transfer system. As you know, when time-varying current flows in the primary coil, and then time-varying magnetic field will be generated. When the secondary coil here is placed in the magnetic field which is generated by the primary coil, voltage is induced at the secondary coil. Here is an equivalent circuit of the magnetic coupled wireless power transfer system. R1 is AC loss resistance, L1 is the self-inductance of the primary coil, C1 is resonance capacitance, and 1,2 means mutual inductance between two coils. AC power source is expressed in AC voltage and the source impedance. By solving this equivalent circuit by simple circuit theory, matching conditions can be obtained as follows. And also, as a maximum coupling efficiency can be expressed as follows. Here, FOM means is a system figure of merit. This is defined as the coupling coefficient kappa and quality factor of Rx and Tx coils as follows. Here, FOM will be also a function of frequency and mutual inductance and also AC resistance of Tx and Rx coils. Intuitively, it's lower loss resistance and higher mutual inductance can give higher FOM and higher coupling efficiency. So it is important to design a coil with lower loss resistance. This slide shows the relation between coupling coefficients C and the Tx and Rx coil specifications, demands. Let's think of two multi-ton rectangular wire coils. The coils are determined by wire diameter A1 and width is large W and height is H and pitch is P and ton number. As you can see, the AC resistance and inductance are changed according to dimensions W1, H1, P1 and A1. Especially AC resistance will be determined by skin effect and proximity effect, which are dependent on coil dimension here. Also, FOM here and the maximum power transfer efficiency are also dependent on directly the dimension of a coil. As I told in the previous slide, the total AC resistance is related to the skin and the proximity effect in metal wires. First, we know Skin effect is that AC current will flow along the surface of the metal wire due to eddy current in higher frequency. Since the total current is the same, however, the area where the current flows is smaller. Therefore, resistance by skin effect will increase. Here, this figure shows the current distribution in metal wire according to frequency. Red is higher current density. As you can see it, as the frequency increases, current density at surface is red, while that in the middle is 0 here. This graph shows the skin depth according to the frequency. As frequency is increased, the skin depth will be decreased, as you can see that. Second, let me explain proximity effect between two wires. Current proximity effect is that the current distribution is changed due to mutual influence of a magnetic field between two neighboring wires. The figure right here shows the current distribution in a single wire. You can see that current distribution is high along the surface due to the only skin effect. However, look at it, figure B. Figure B shows that current distribution will be changed due to the proximity effect. You can see that the area will be reduced while total current is the same. Therefore, is total AC resistance increased. This case is rectangular coils. Let me explain later. Here is a multi-turn wire coil. To optimize the coil of a multi-turn circular wire coil with a minimum resistance to considering the skin and proximity effect, we considered first parallel straight wires conductors. As you can see, the cross-section of the multi-turn wire coil is similar that of the parallel straight wire conductors. And so, by calculating the parallel straight wire conductor, and the result can be applied for the design of a multi-turn circular loop coils. Here the simple configuration of 4 parallel wire conductors. P is a pitch between two neighboring conductors. The radius of the wire is R0. The current I0 in each wire will flow in the same direction. For the conductors, the total AC resistance R ohmic can be obtained by the sum of resistance by skin and resistance by proximity. R skin is defined by RTC and skin depth delta and wire radius as R0. RTC is defined as here. R proximity is AC resistance by proximity effect. It is defined here. I0 means, as I told you before, the current in the wire conductors. Hz means the magnetic field which is generated by current I0 of the neighboring wires. As you can see, that to calculate the R proximity, we have to find the Hz. This figure shows how to calculate it, how to derive, how to obtain the Hz from the line source I0. Let me explain how to derive the H field in next slides. Now, let me define the proximity factor Gp. Gp is the ratio of R proximity over R skin. And finally, we can derive the Gp is expressed as these equations. I have to emphasize that when you want to calculate GP, we have to calculate the magnetic field. So I would like to say that when you want to calculate the ohmic, we have to calculate the magnetic field, the H field. It is very important to calculate the H field. Now, let me explain how to obtain the magnetic field. Look at these figures. There are two wires. One wire is equivalent to line sources. And the question is, what is the magnetic field which is generated by line sources? By Ampere's laws, Hg can be derived as follows. For example, phi is 19 degree, Hg is simplified as follows. This figure shows the normalized Hg field on a wire versus phi with a different pitch. As you can see, the Hg is varied according to phi. So that to calculate the magnetic field also is AC resistance, we choose medium Hg field, not the whole magnetic field at each angles. This figure shows the M parallel wires. To calculate the H field of the HM in the M parallel wires, we can able to consider the two cases. One is a symmetric case, is a pair, and the other is asymmetric groups. First, here is asymmetric cases. Asymmetric case is phi is varied from 0 to 180 degree. So we would like to choose the medium Hg at phi. Second, we think about the Hg for us symmetric cases. Is wire A can be affected by the both left C line source and the right B line source. That is, the Hg field can be obtained as calculating H beta and H gamma. H beta and H gamma are expressed as followed here. Now let me explain how to obtain the total H field at the mth wire made by the m-e wires. Hm is the sum of Hm pair, means it's a symmetric case, and Hm a symmetric case. Total Hm can be expressed as follows. Finally, we can obtain the total ohmic resistance by M parallel wires. And our ohmic is like that. Our ohmic is expressed as follows, and the Hm is replaced by this Hm, and then we can get a total ohmic resistance. First, the calculation method is verified with the previous reference. The reference is here. This graph shows the proximity factor Gp according to P of 2R0 with a different number of n. In case of M parallel straight conductors, the calculation is a dashed line and the reference is a solid line. I would like to say that calculation is in good agreement with the reference. Also, as the number of conductor n increase and the P of 2R0 is lower, proximity factor P increase dramatically. That is, AC resistance will also increase dramatically. For mole calculation, we can derive an optimal design rule for minimum AC resistance. This graph shows that the optimal R0 of large W, according to a number of n. Large W means is the total width of n parallel state wires. As you can see, that each turn has optimal R0 of large W. By curve fitting of this graph, R0 of W is determined as a function of N for lowest AC resistance. I would like to emphasize that these equations can be applied to design circular or rectangular wires coils for lowest resistance. These coils can be designed for lowest resistance. For verification of the calculation method, we made several helical coils. As you can see, that the cross-section of the helical coil here is similar to that of the parallel state wires conductors. The coil has a different pitch and turn number of 6, and radius is 45 millimeter. The frequency is 6.78 megahertz. The result here shows that R0 is larger until 0.65 millimeter here, about here. AC resistance will be lower, since second resistance will be reduced quickly, even though the proximity factor will increase slowly. However, R0 is thicker than is 0.7. AC resistance will be higher again, since proximity factor will increase rapidly. This graph shows that the calculation and simulation by ANSYS Maxwell are in good agreement. Also, the measurement is similar to the calculation. We also investigate that a coil which is optimized for lowest resistance will have a better efficiency, coupling efficiency. This coil here is optimized for the low resistance in terms of wire radius R0. The other is not optimized. From the measurement, the optimal coil have a better coupling efficiency. Especially, Z is larger, and the efficiency is better than the case of the coil which is not optimized. So it means the optimized coil will have a better coupling efficiency. Now let's think of calculation of printed circular and rectangular spiral coil and printed straight parallel conductors. For the first time, we will consider the calculation of AC resistance of planar multi-straight parallel conductors. To calculate the AC resistance of printed coils and the parallel state conductors, we use the volume filament model. Here is the procedure of a volume filament model. The main concept of volume filament model is to solve a problem in circuit domains, not solving Maxwell equation directly. Let's think of a straight conductor with an arbitrary cross-section. The conductor is discretized as is shown here. Here are two filament wires of a square cross-section here. two filamentars are coupled inductively. Now we can find an equivalent circuit for the conductors. It's like that. Each filament can be equivalent to inductance and AC resistance. Finally, by solving the equivalent circuit, the total resistance and inductance are solved. For volume filament model, it is important to discretize a target coil. Here we consider the three cases of printed parallel straight conductors, a printed circular spiral coil, and a printed rectangular spiral coil. For the parallel straight conductors here, the conductor is discretized in a finite scale line here. For the circular coils, it is discretized in a loop with a finite thickness. For rectangular coils, it is discretized in a rectangular width here is a finite thickness. And by discretizing these coils properly, we can solve the coils efficiently. This slide shows an equivalent circuit of M parallel state conductor here. Each conductor is discretized in N filament straight lines. Each filament line with a finite thickness is expressed as resistance and inductance. And then each conductor has N filament loops as N resistance and inductance. By applying Kirchhoff voltage laws, we can formulate the equations of this equivalent circuit. It means is Vt is equal to the impedance matrix times is current It. Is It and Vt are defined as follows, and Ik and Vk are defined as follows. By assuming that all current at each conductor flows 1 amperes, and then we can obtain the resistance as real of Vt, and inductance is imaginary of Vt over omega. Omega is 2 pi f. This slide shows a detailed explanation of calculation. As you can see, there is a voltage matrix and impedance matrix and the current matrix. And then the whole matrix can be expressed as follows. And here, there's X is impedance matrix. Impedance matrix can be expressed as follows. Here, there's R is RDC, and is M is mutual inductance between two wires. And then from the derivation of this matrix, and then we can get to the solution Vt, and then finally we can get resistance and the inductance as follows. In the previous slides, impedance matrix is very important to calculate AC resistance. Impedance matrix consists of RDC and mutual inductance. Therefore, mutual inductance calculation is very important to calculate AC resistance. Now, I would like to show on some example to calculate the mutual inductance in some cases. First, I will show the two rectangular wires which are arranged in arbitrary angles. The mutual inductance can be calculated as follows. M12 is that. There are two methods. The first method is to use magnetic flux here, Bm, and the DSM. And the second method is to use vector magnetic potential. And the detailed derivation is referred to the reference here. Now, let me give another example of a mutual inductance calculation between two loops in an arbitrary position, two loops in arbitrary positions. M is calculated as follows. Here, the whole parameter we defined is as follows here. I would like to recommend that if you need more information, more explanation, please refer to this reference. By using the volume filament model method, first we calculate current distribution for a single printed conductor here. Here is the conditions for the calculation. This figure shows the current distribution according to the large Wn. The pollution frequency is 6.78 megahertz. From the calculation, it is true that most current will flows along left and right end. Also, current flows along the upper and down line of the wires. Left graph here shows the circuit resistance is displayed. Circuit resistance is displayed according to the large Wn, which is normalized by skin depth with the frequency 6.78. From the graph and the current distribution, as the large Wn becomes larger, here, current density is slightly lower, also AC resistance is lower. Now, by using volume filament model, we calculate the AC resistance for the case of one-dimension printed parallel-state conductors as follows. Each conductor will be discretized is a small straight conductor with a finite thickness. This figure shows the n parallel straight conductors. As a metal, we use copper. Thickness of metal is 70 micrometer, is about 2 ounces. Frequency is 6.78 megahertz. Total width of the conductors is varied from the 10 millimeter to the 30 millimeter. This graph shows the resistance normalized by Rm. Rm means average resistance when W0 over large W is 0.05 here, with a different number of conductors. As you can see in the graph, at each number of n, the optimal W0 of large W for lowest resistance exists, regardless of large W with W. The reason of the optimal relation of W0 over W is that when W0 over W0 over large W is higher than optimal W0 over W with a fixed, with the W, large W is fixed, our norm will increase since two neighboring conductor is getting closer, and then proximity factor will increase. When W0 over large W is lower than optimal W0 over large W, our norm is also increased since here, for example, is N6 is large, the small W0 of W is lower, since the skin resistance will give an effect on resistance directly. We also derive an optimal design formula for lowest resistance. This graph shows the optimal small w0 of large W according to N. For lowest resistance, the optimal relation will be applicable for frequency between 2 MHz and 27 MHz. Also, metal thickness here between 1.4 skin depths and 5 skin depths. As you can see, that each number of n, we can find the optimal W0 of over large W's. By curve fitting method, we can get a design formula for the minimum loss. It's like that. W0 over W is a function of a number of n. For verification of optimal relation R0 over large W, total pattern widths, we fabricate several printed spiral coil with a diameter is 16 centimeter. Here are the specification of the fabrication coils here. Total pattern width large W is 2 centimeter. Turn number is 5. The optimal pattern width of each conductor at 6.78 MHz is about 3.4 millimeter. This graph shows measured resistance according to each pattern width with 2 MHz and 6.78 MHz and 10 MHz. The dashed line are calculation and solid line here are measurement. As you can see that the coil of 3.4 millimeter pattern width has the lowest resistance for the frequency. It is verified for the optimal relation which is provided in the previous slide. Now the proposed method is applied to calculate the AC resistance of the printed circular coils. For calculation, a printed spiral coil is equivalent to a concentric multi-circular loop coil. To apply the volume filament model method for coil analysis, each conductor is discretized in finite thick loops here. This slide shows the calculation of result of current distribution and the resistance and inductance for a printed circular coil. The specification of the coil are 3 tons and pattern width is 0.4 millimeter, metal thickness is 0.2 millimeter. Pitch from center to center is 1 millimeter, frequency is 6.78 megahertz. For comparison, the same coil is analyzed by ANSYS Maxwell 2D. First, calculate resistance and inductance are compared with them. Both results are in good agreement. Here are current distribution. Maximum current distribution is red and blue is the zero current distribution. See B loop current distribution here. Since the conductor is symmetric, the current distribution in a B loop is symmetric, and the more current will flow along 4 edges. However, see loop A and C, current flows near left upper edge and down edge at loop A. At loop C, result is different. I would like to say that skin effect will make the current flow along edges, and the proximity effect will make the current flows near 2 edges. Therefore, it is necessary to optimize a coil for better efficiency, that is, to find the optimal patterns with W0, total width, total pattern width, large W, turn number, and metal thickness with the coil diameter fixed and the metal thickness is fixed. Now let's think of calculation of printed rectangular coils here. For calculation, a printed rectangular coil is equivalent to a concentric multi-rectangular loop coils. To apply the volume filament model for the coil analysis, its conductor here is discretized in a finite thick rectangular loops. We apply the method to design the coil of maximum Q factor with a metal thickness, and the coil width and length are fixed. For more detailed explanation, please refer to the following reference paper. To optimize a coil, the coil's width and the metal thickness are fixed. A coil width is 2 cm, metal width is 150 micrometers are fixed in this example. For the cases of W0 is 0.2, 0.4, 0.6, and 3 coils are optimized for the case, and the turn numbers and the gap between 2 neighboring patterns are determined. Here are photographs of the 3 optimized coils for 3 cases W0. For comparison, we made several coils. This graph shows the Q factor of coils which are calculated by using measured resistance and the inductance. As you can see, the calculation are in good agreement with the measurement. Also, the optimized coil have the highest Q factors. It is also interesting that coils with more than optimal turn number here have lower Q factor. The reason is that this case has higher proximity factor. In my talk, AC resistance calculation by considering skin and proximity effect is explained, and the method is applied for optimization of an effective coil in magnetic coupled wire power transfer, especially in the megahertz frequency range. Especially the calculation method for parallel straight wire conductors is presented in approximate closed form. It is shown that the result can be applied for an optimal design of effective helical coil. We also provided an optimal relation between R0 of large W and the turn number for lowest resistance here. Also, volume filament model is explained shortly. By using volume filament model, printed parastate conductor are analyzed. From analysis, it is found that the optimal ratio between each pattern width and the total pattern width can be obtained for each turn numbers here. Finally, we show that the method will be able to design the coil of maximum Q factor with metal thickness and the coil width and the length are fixed. Before I finish my presentation, let me introduce a special issue, next generation wireless charging system for mobile devices. Deadline is the 1st April 2021. Please refer to the website for more detailed information here. I appreciate potential authors who will submit the valuable research articles and results. Thank you so much.